The universe is vast and full of mysteries, one of which is the possibility of extraterrestrial life. Imagine the unending cosmos, a space so immense that it boggles our mind, a realm humming with countless stars, planets, galaxies, and perhaps life forms we've yet to discover. Our curiosity and scientific spirit have spurred us to delve into these enigmatic depths, to uncover the secrets they hold. And one of the tools we use to unravel this cosmic mystery is the Drake equation. The Drake equation was born in the summer of 1961, crafted by the astrophysicist Frank Drake, not for the purpose of quantifying the number of civilizations, but intended to stimulate scientific dialogue at the first scientific meeting on the search for extraterrestrial intelligence, also known as SETI. Frank Drake, a young astrophysicist at the National Radio Astronomy Observatory, was preparing to host a conference that would gather the brightest minds to discuss the possibility of intelligent life beyond Earth. But how could such a broad and speculative topic be discussed in a structured and scientific manner? The answer was the Drake equation. Frank Drake formulated this equation as a way to break down the vast concept of extraterrestrial life into manageable parts. Each variable in the equation represents a factor that would influence the number of communicative civilizations in our galaxy. These variables range from the rate of star formation to the likelihood of intelligent life developing. Interestingly, Drake never intended for his equation to churn out a definite number. Instead, he saw it as a tool for thought, a way to shape and guide the discussion. It was about asking the right questions, not necessarily finding the exact answers. The conference, held at the Green Bank Observatory in West Virginia, was the first of its kind. The Drake equation was presented as the opening topic, setting the tone for the discussions that followed. It was a call to approach the search for extraterrestrial intelligence with a scientific mindset, to ask hard questions and to seek evidence-based answers. The impact of the Drake equation was immediate and far-reaching. It provided a framework for the SETI research, prompting scientists to think deeply about each of the factors and how they might be determined. More than just a mathematical formula, it was a catalyst for scientific curiosity and exploration. And so, the Drake equation became a fundamental tool in our quest to understand our place in the cosmos. The Drake equation, at its core, is a probabilistic argument used to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. Let's break down this fascinating equation into digestible chunks. The equation begins with n, the number of civilizations with which we could potentially communicate. To estimate n, we must first consider r*, the average rate of star formation in our galaxy. Picture a vast cosmic nursery, birthing stars at a constant rate. Next, we have FPR, the fraction of those stars that have planetary systems. Imagine a celestial family with planets orbiting their parent star. Not every star has this privilege, and FP helps us quantify this. Moving on, we encounter NE, the average number of planets that could potentially support life per star that has planets. Think of planets in the Goldilocks zone, where conditions are just right for life as we know it to exist. FL is our next variable, the fraction of the above planets where life actually develops. This is where the magic happens, where life sparks amidst the cosmic dust. Phi follows, representing the fraction of life that evolves into intelligent beings. Picture an alien Einstein pondering the mysteries of the universe on a distant world. FC is up next, the fraction of civilizations that develop a technology that releases detectable signs of their existence into space. Imagine a distant civilization sending out radio waves or laser pulses hoping to be heard. And finally, we have L, the length of time for which such civilizations release detectable signals. This is the cosmic lifespan of a communicative civilization, a testament to their resilience or perhaps their downfall. It's fascinating, isn't it? Each variable, each factor in the equation gives us a glimpse into the vast, complex puzzle of the cosmos. From the birth of stars to the lifespan of advanced civilizations, the Drake equation encapsulates the profound question of our place in the universe. Each factor in the equation adds another layer of understanding to our quest for extraterrestrial life. Opening. The Drake equation has been instrumental in the search for extraterrestrial intelligence, or SETI. The Drake equation, in essence, is a roadmap for the quest of extraterrestrial intelligence. It provides a systematic approach to estimate the number of civilizations in our galaxy capable of interstellar communication. This equation is the backbone of SETI, shaping its strategies and guiding its research. Let's delve a bit deeper. The Drake equation is not just a mathematical formula, it is a philosophical statement. It acknowledges the possibility that we are not alone in this vast cosmic sea. This perspective has widened the horizons of SETI and other similar efforts to find extraterrestrial life. SETI's primary method, for instance, involves listening for radio signals from space, a strategy directly influenced by one of the terms in the Drake equation, the fraction of civilizations that develop a technology that releases detectable signs of their existence into space. Now, what about the results and implications of the equation? Well, the Drake equation, with its multiple variables, has given a wide range of answers, from a pessimistic view of us being alone to an optimistic scenario of millions of civilizations. But here's the catch. We still don't have definitive values for many of the equation's variables. So the equation serves more as a tool to guide our thinking and our search strategies rather than providing an exact answer. It encourages us to explore, to learn, and to understand the universe in its entirety. In the grand scheme of things, the Drake equation underscores our desire to know if there's anyone else out there. It represents our curiosity, our longing for connection, and our drive to explore the unknown. It reminds us that we are a part of a larger cosmic story, and our search for extraterrestrial life is a search for our place in the universe. Closing. Through the Drake equation, we continue to probe the depths of the cosmos, seeking answers to our most profound questions. Despite its age, the Drake equation continues to hold sway in our understanding and exploration of the universe. A testament to its enduring relevance, it continues to be a tool in our cosmic toolbox, helping us navigate the vast seas of the universe in our quest to answer the age-old question, are we alone? In recent years, the Drake equation has found applications beyond its original purpose. It's being used to guide our choices in sending spacecrafts to potentially life-harboring planets. The Kepler Space Telescope, for example, has identified thousands of exoplanets, some of which fall in the Goldilocks zone, not too hot, not too cold, but just right for life as we understand it. And these discoveries were guided in part by the principles of the Drake equation. But as we make new discoveries, our understanding of the variables in the equation evolves. Take the variable FLE, for instance, which represents the fraction of planets that develop life. With advancements in astrobiology, we've come to realize that life may be more resilient and adaptable than we once thought, potentially existing in environments far different from our own. This expands the possibilities for FETL, and by extension, the number of civilizations that may exist in our galaxy. On the horizon, future missions like NASA's James Webb Space Telescope promise to further refine our understanding of these variables. With its unprecedented sensitivity, it will be able to detect the chemical signatures of life on distant exoplanets, providing us with more data to feed into our Drake equation. Yet, as our understanding evolves, so does the Drake equation. It is not a static formula, but a dynamic reflection of our ever-growing knowledge about the universe. As we learn more about the cosmos, the equation adapts, changing and growing with us. It's a living testament to our ongoing scientific journey. Critics may argue that the Drake equation is too simplistic, that it can't possibly account for all the complexities of the cosmos. But that's missing the point. The Drake equation is not about precision, it's about possibility. It's about giving us a framework to explore the potential for life beyond our planet. It's about sparking our curiosity and driving us to ask more questions, to explore further, to reach for the stars. As we continue our cosmic journey, the Drake equation remains a beacon, guiding us towards the tantalizing possibility of discovering extraterrestrial life.